Right now, something extraordinary is unfolding above us. September 2025 has delivered a barrage of near-miss encounters that's left astronomers stunned. Asteroid 2025 FA22 will hurtle past our planet at just over twice the moon's distance, while 2025 RJ2 screams even nearer, less than 300,000 kilometers from Earth. Dozens of smaller space rocks are being detected at distances closer than the moon in a single record-breaking week. Simultaneously, 3I/Atlas, a chemically anomalous visitor from interstellar space, accelerates toward Mars on a path unlike anything archived in the Minor Planet Center's extensive database. The statistical improbability is staggering. Are we witnessing random cosmic chance? Or is there an underlying pattern that could fundamentally alter our approach to planetary defense? The implications could transform humanity's role from passive observer to active participant in solar system dynamics. September 2025 opens with an unprecedented cascade of alerts. Scientists at the Minor Planet Center document asteroid 2025 FA22 at approximately 2.2 lunar distances, roughly 835,000 kilometers away. Just 3 days prior, 2025 RJ2 streaked past even closer, at a mere 0.78 lunar distances, or under 300,000 kilometers. These aren't random, isolated occurrences. The 7-day period from September 12th to 18th obliterates every previous record. No fewer than 28 near-Earth objects penetrate the moon's orbital sphere. That's 3 times the previous weekly maximum. The majority measure between 8 and 25 meters across, the category that typically disintegrates in our atmosphere or produces explosive airbursts similar to the Chelyabinsk event. However, 2 objects, FA22 and RJ2, are substantially larger, with estimated diameters reaching 120 meters. These demand worldwide vigilance and tracking. Each new detection lights up monitoring stations globally. Pan-STARRS in Hawaii, Atlas operating in Chile, the Rubin Observatory in Chile's Atacama Desert, and Catalina Sky Survey in Arizona all contribute to the flood of data. Automated telescopes sweep the heavens continuously, their software calibrated to identify even the dimmest, fastest-traveling objects. The discovery pace is breathtaking. Fresh objects are identified, trajectories calculated, and entries logged, sometimes within mere hours of initial detection. The Rubin Observatory, operational for only months, has revolutionized detection capabilities. Its expansive field camera surveys vast sections of sky in systematic sweeps, capturing objects that would have remained invisible just 12 months earlier. From a statistical standpoint, this surge should be a once-per-century anomaly. Population models, adjusted for observational biases, calculate the probability of detecting over 25 sublunar near-Earth objects in 1 week at less than 1 in 1,500. Despite dramatically improved detection technology, September's cluster remains exceptional. It defies the expected random distribution of asteroid approaches. Various experts theorize about orbital resonances, or perhaps an undiscovered fragmentation event deep within the asteroid belt, though most attribute the phenomenon to technological advancement. Detection efficiency now surpasses 90% for objects exceeding 20 meters within 1 lunar distance. Observational blind spots are contracting, though not eliminated entirely. Approaches from the sun's direction remain problematic, a vulnerability burned into collective memory by the Chelyabinsk airburst 12 years ago. On social platforms, the data triggers widespread speculation. Graphs circulate displaying a spike that appears statistically improbable. Some label it orchestrated. Others whisper about warning signals. Within scientific communities, the atmosphere is cautious yet heightened. Every close passage receives meticulous analysis and archival documentation, strengthening a planetary defense infrastructure only as robust as its most recent detection. For a fleeting moment, global attention shifts skyward, and one question persists: what if even a single one of these objects had been aimed just slightly more directly at us? Imagine FA22 hadn't missed. At 120 meters in diameter, roughly equivalent to a city block's height, the asteroid's atmospheric entry would commence high above the surface, an invisible speck traveling over 18 kilometers per second. If composed of stone, like most objects in its size range, It would compress atmospheric gases ahead of it until mounting pressure triggers catastrophic fragmentation in a violent airburst, reminiscent of Chelyabinsk in 2013. But scale is everything. Chelyabinsk's shockwave shattered windows throughout 6 cities and sent more than 1,500 people seeking medical attention, primarily for lacerations from flying glass and concussions. FA-22 carries over 20 times that destructive energy. A stony asteroid of this magnitude could detonate at altitudes between 10 and 20 kilometers, unleashing energy equivalent to multiple megatons of TNT. The resulting shockwave would demolish buildings across dozens of square kilometers. Anyone within the blast epicenter would have mere seconds, perhaps less, to respond. Windows would explode inward, structural walls would crumble, and the intense thermal flash could ignite flammable materials on rooftops across the impact zone. The destruction wouldn't be confined to ground zero. Surrounding neighborhoods would experience the blast's fury through airborne debris and collapsing infrastructure, exponentially multiplying casualties. If FA-22 were iron-based, the scenario transforms completely. Iron asteroids possess greater density and structural cohesion. Rather than fragmenting, an iron body could penetrate the entire atmosphere, striking the surface at nearly its original velocity. The outcome: a crater measuring hundreds of meters across, a fireball visible across vast distances, and an ejector plume driven into the stratosphere. While the immediate impact would obliterate local infrastructure, the environmental consequences could propagate much farther depending on impact location. Now consider an ocean impact. More than 2/3 of potential strike zones are water-covered. Here, the energy transfers into a colossal steam plume accompanied by a series of radiating tsunami waves. Though much of the wave energy dissipates rapidly in deep ocean waters, coastal regions within several hundred kilometers could face water walls reaching tens of meters high. Ports, coastal cities, and low-elevation islands would confront catastrophic inundation with minimal advance warning. The Chelyabinsk event exposed our critical vulnerability. Objects approaching from the sun's direction remain invisible to ground-based telescopes until the final moments. Sergei Karpov, whose dashboard camera footage became iconic documentation of that morning, continues to describe the aftermath in terms of overwhelming noise, shattered glass, and mass confusion. Years later, he collaborates with disaster response organizations, advocating for cities to conduct rehearsals for events that provide no warning. His central message is stark. The boundary between a harmless fireball and an urban annihilating disaster is far thinner than most people comprehend. In post-flyby simulations, the numbers paint a sobering picture. Impact energy calculations, population density assessments, time of day variables, all factors in a cosmic equation that unfolds without intention or malice. Our sole defense lies in vigilance, early detection, and the systems that transform warnings into protective action. Without these safeguards, the cost is quantified in devastated cities and permanently altered lives. Comet Swan presents an entirely different spectacle. Discovered on September 11, 2025, not through traditional optical telescopes, but via the Solar Wind and Isotropies SWAN instrument aboard the SOHO spacecraft. This comet's arrival was heralded by a dramatic surge in hydrogen emissions. The Lyman alpha glow, an ultraviolet signature invisible to human eyes, illuminated data streams before most ground-based observers realized there was something to observe. A small group of amateur astronomers scanning the Virgo constellation independently confirmed what satellite instruments had suggested. Swan was brightening rapidly, its tail doubling in length during a single night. This wasn't merely about visual brightness. Spectroscopic analysis revealed a volatile-rich coma dominated by hydrogen with notable quantities of cyanogen and various carbon compounds. The outgassing rate accelerated dramatically as the comet approached perihelion, with hydrogen production exceeding water vapor by a ratio that surprised even veteran comet observers. The explanation: Swan's icy nucleus was fragmenting under intense solar heating, exposing pristine layers and releasing trapped volatiles in successive outbursts. Each fresh fracture in the nucleus triggered another round of hydrogen flares detectable by ultraviolet-sensitive instruments. Professional observatories rushed to schedule follow-up observations. The Rubin Observatory, still optimizing its survey protocols, allocated emergency observation time to track the evolving coma. Meanwhile, citizen scientists maintain their data contributions, timing outburst events, mapping tail morphology, and flagging sudden brightness variations. Their real-time alerts help direct high-resolution spectrographs toward fleeting phenomena, material jets arcing from the nucleus, subtle chemical composition shifts, and telltale indicators of structural stress that frequently precede complete fragmentation. As September progressed, fragmentation risk intensified. Recent computational models indicated that Swan's nucleus, already riddled with fissures, might not survive its closest solar approach intact. A complete breakup would generate a spectacular debris cloud visible from both Earth and orbital platforms. For planetary defense teams, Swan's volatile behavior reinforced a critical lesson. Not every threat travels on silent, predictable trajectories. Sometimes the first warning arrives as an unexpected hydrogen burst, detected by a global network of amateur astronomers with their instruments trained skyward. April 13th, 2029 is already marked in bold on every planetary defense calendar. On that date, asteroid Apophis will pass just 32,000 kilometers from Earth's surface, closer than numerous communication satellites orbit, and will be visible to unaided eyes as it sweeps across the sky. For years, Apophis dominated doomsday headlines, labeled potential planet killer, when first identified in 2004. However, subsequent observations eliminated the impact threat, replacing fear with extraordinary scientific opportunity, a live planetary defense rehearsal with global observation and comprehensive instrumentation ready. This close approach offers more than spectacular viewing. Earth's gravitational field will exert measurable forces on Apophis, creating tidal effects not in water, but in rock and dust. Scientists anticipate observable changes. Surface landslides triggered by gravitational stress, regolith particles shaken loose, possibly even measurable alterations to the asteroid's overall shape. These tidal phenomena have never been documented up close on an object of this size. It represents a natural experiment impossible to replicate in any laboratory setting. To capture these transformations, NASA has deployed OSIRIS-APEX, a spacecraft tasked with rendezvous with Apophis shortly after flyby. Its mission objectives: document every surface alteration, every displaced boulder, every trace of Earth's gravitational influence. The before and after imagery will reveal how asteroids respond to close planetary encounters and how minor gravitational perturbations can alter a space rock's trajectory. For Andrea Riley, a systems engineer on a HERO team, the approach carries profound personal significance. In a 2022 diary entry, she recalls the anxiety of watching Apophis dominate news cycles as a teenager. That sense of existential dread, tempered by emerging technological solutions, now drives her professional work. Apophis represents more than a scientific test subject for spacecraft and scientists alike. It's a comprehensive dress rehearsal for humanity's capacity to track, model, and, if circumstances ever demand, deflect a genuine threat. Every calculation, every observation, every line of code written for OSIRIS-APEX or ground-based radar systems advances us toward a future where close encounters are met with composed precision rather than panic. As Apophis races past, the world witnesses planetary defense in action, transforming a headline once dominated by fear into a narrative of preparedness and discovery. Comet 3I/Atlas, officially cataloged as C/2025N1, distinguished itself from the first spectroscopic analysis. On July 1st, Pan-STARRS identified its hyperbolic trajectory, but the chemical composition sent scientists scrambling for observation time on the world's premier telescopes. Early Very Large Telescope, VLT, X-shooter data, captured as the comet crossed approximately 4.4 astronomical units, revealed a coma dominated not by water vapor, the typical comet signature, but by carbon dioxide. The James Webb Space Telescope confirmed these remarkable findings in August. Carbon dioxide production measured 129 kilograms per second, while water vapor trailed far behind at merely 6.6 kilograms per second. That a ratio approaching 20-1, unprecedented for a comet exhibiting this level of brightness and activity. For context, most solar system comets display the inverse ratio, with water outgassing dominating carbon dioxide by substantial margins. Here, conventional patterns are completely reversed. The anomalies extend beyond volatile composition. High-resolution spectra from a VLT's ultraviolet instrument, collected over multiple nights in July and August, detected a robust atomic nickel signal, 4.6 grams per second streaming from the coma as of August 21st. Yet iron, nickel's nearly universal companion in cometary chemistry, was conspicuously absent, remaining below detection thresholds. This nickel without iron pattern is exceptional even among interstellar visitors. In solar system comets, nickel and iron invariably appear together, liberated by identical heating processes. Competing theories range from unique formation chemistry to selective iron loss during billions of years of interstellar drift. Some researchers point toward the breakdown of nickel-rich organic compounds. Others propose cosmic ray weathering progressively stripped away more volatile iron-containing molecules. No single model comprehensively explains all observations yet, but scientific debate remains intense and ongoing. Mid-August delivered another surprise. The Mars Reconnaissance Orbiter, monitoring ultraviolet wavelengths, detected a sudden flare, an outburst that doubled the comet's brightness in under 36 hours. Ground-based photometry revealed the tail splitting into multiple distinct components, with dust streaming in separate directions. These episodic eruptions don't align with typical water-driven jet behavior. Instead, they suggest pockets of carbon dioxide or alternative volatiles erupting as solar radiation penetrates fresh fractures. Rotation studies compound the mystery. Light curve analysis indicates a slow, possibly tumbling nucleus spinning on an axis that shifts over time. The rotation period exceeds 22 hours with minimal brightness variations, evidence suggesting either a nearly spherical shape or complex non-principal axis rotation. This makes predicting outbursts and tail evolution exceptionally challenging. Each new dataset adds complexity to the puzzle. With perihelion scheduled for October 29th, the world spectroscopists are engaged in a race against time to record every detail before the comet disappears behind the sun. For now, 3I/Atlas remains a chemical outlier, a slow-spinning messenger from a colder, darker region of the galaxy, carrying secrets about conditions and chemistry in distant stellar systems that we're only beginning to decode. The first anomaly appeared on October 14th, 2 weeks before 3I/Atlas would reach perihelion. Dr. Sarah Chun was reviewing trajectory calculations at the Minor Planet Center when her terminal flagged an irregularity. The comet's path had shifted, minutely but measurably, not the gentle curve of solar gravity, but something else, something that made her coffee go cold in her hand. "Run it again," she told the system. The numbers didn't change. Within hours, observatories worldwide confirmed it. 3I/Atlas was decelerating in a way that violated every model of cometary behavior. The carbon dioxide jets weren't random outgassing. They were firing in coordinated pulses, adjusting trajectory with impossible precision. Andrea Riley saw it first. Working late on OSIRIS-APEX preparations for the Apophis encounter, she overlaid September's asteroid detection data with 3I/Atlas's trajectory. Her hand froze on the mouse. The September surge wasn't random at all. Every single near-Earth object that week, all 20 of them, had passed through precise orbital positions, not where they intersected Earth's path, but where they intersected each other's paths. The asteroids had formed a three-dimensional lattice in space, a geometric pattern spanning millions of kilometers, and 3I/Atlas was heading directly toward the lattice's focal point. She pulled up spectroscopic data with shaking hands. The nickel signal, that inexplicable nickel without iron signature. She'd seen something similar before in classified briefings about deep space probe telemetry. The isotope ratios match refined, processed metal, not natural ore. Riley reached for her phone. "We need to convene the Planetary Defense Coordination Office. Now." By October 22nd, the story had escaped containment. Social media erupted with leaked telescope images showing 3I/Atlas's latest outburst. Except this time, the tail had split into 6 perfectly straight lines, each aimed at a different region of space. Amateur astronomers tracked them obsessively. One line pointed toward Mars, another at Jupiter's orbit, 3 toward deep space coordinates that meant nothing to the public, but everything to NASA's Deep Space Network operators. The 6th line pointed directly at Earth. Governments issued contradictory statements. The European Space Agency urged calm, while frantically repositioning satellites. China went dark, their space program radio silent for 72 hours. Russia announced they were monitoring the situation with appropriate measures. In orbit, the International Space Station crew received sealed orders and began moving critical equipment to the station's shielded modules. On October 24th, Comet Swan, still fragmenting, still outgassing hydrogen in spectacular bursts, did something unprecedented. Its trajectory shifted, not toward the sun as model predicted, but perpendicular to the ecliptic plane, accelerating upward as if climbing an invisible staircase away from the solar system's disk. The hydrogen wasn't outgassing. It was propellant. October 29th arrived with every major telescope on Earth aimed at the same point in space. The Rubin Observatory canceled its survey schedule. Amateurs and professionals alike held their breath as 3I/Atlas reached its closest approach to the sun. At precisely 14:22 Universal Time Coordinated, the comet stopped, not decelerated, stopped, dead still in space. 39 cent from the sun, it hung motionless against the stellar background for 17 seconds that felt like 17 lifetimes. Then it bloomed. The carbon dioxide coma collapsed inward, pulled by forces that made no sense, compressing into a sphere of such intense brilliance that automated telescopes globally shut down their imaging systems to prevent sensor damage. When the light faded 3 minutes later, 3I/Atlas was gone. In its place hung a structure. It was spherical, roughly 800 meters in diameter, its surface a lattice of the same geometric pattern the September asteroids had traced. Through gaps in the structure, something moved, machinery or perhaps biological forms, impossible to distinguish at this distance. The nickel signature blazed stronger than ever, accompanied now by iron, chromium, exotic isotopes that existed nowhere in the solar system's natural inventory. As Earth's instruments struggled to process what they were seeing, the structure rotated. Panels realigned with mechanical precision, and then it began transmitting. Not radio waves, not laser pulses. Something older, something that bypassed the electromagnetic spectrum entirely and imprinted directly onto quantum-entangled particles in Earth's upper atmosphere. Every physics laboratory with particle detectors received the same message simultaneously, the data materializing in their systems without passing through any receiver. The transmission was mathematical, a three-dimensional schematic showing the structure's interior, with one section highlighted and marked with a symbol that appeared in every human mathematical notation, an equal sign flanked by a question mark. An invitation? A test? A warning? Andrea wryly stared at the decoded message on her screen, tears streaming down her face. The Apophis encounter was still 5 months away, but suddenly that dress rehearsal felt desperately inadequate. Swan accelerated away from the solar system, its hydrogen jets blazing a path toward interstellar space, its mission, whatever it had been, apparently complete. The September asteroid began showing nickel signatures of their own, and in the cold mathematics of the transmission, buried in the schematic's recursive geometry, Dr. Chen found something that made her blood run cold. A countdown. 23 days, 7 hours, 14 minutes. When it reached zero, the structure would move again. Its trajectory, already calculated by every supercomputer NASA could commandeer, was absolute and unalterable. It was coming to Earth, not to impact, not to threaten, to dock. The age of passive observation had ended. Humanity's role in solar system dynamics was about to change forever, whether we were ready or not. Above us, against the vast darkness, the structure waited for an answer to a question we'd only just learned to ask. Retry. A. Continue. The UN Security Council met in emergency session for the 3rd consecutive day, but the real decisions were being made 400 kilometers above them. Aboard the ISS, Commander Elena Volkov floated before an observation window, watching the structure, now officially designated artifact, one in sterile bureaucratic fashion, maintain its perfect stillness against the sun's glare. 22 days, she murmured into her headset. Andrea, tell me you've made progress. In Houston, Riley hadn't slept in 60 hours. Her team had grown from 5 people to 50, crammed into a mission control room never designed for the scenario. The walls were papered with printouts of the quantum transmission, each one marked with competing interpretations in different colored ink. The equal sign isn't asking if we understand mathematics, Riley said, her voice hoarse. It's asking if we're equals. The question mark, it's asking if we want to be. And the highlighted section? Volkov asked, an airlock or something analogous. It's showing us where to meet them. Across the room, Dr. Chin looked up from her terminal. We've got movement. The structure just rotated 30 degrees on its vertical axis. It's facing Earth now, directly facing us. While world leaders argued about protocols and sovereignty, a different kind of coordination was taking shape. Sergei Karpov, the Chelyabinsk survivor who'd spent 12 years advocating for planetary defense, received an encrypted message on his phone at 3 a.m. Moscow time. The sender was anonymous, but the message was clear. Check asteroid 2025 RJ2. Check them all. Within hours, amateur astronomers worldwide were training their instruments on the September surge asteroids. What they found rewrote everything. The asteroids had formed a network, a relay system. Each one pulsed with faint nickel emissions at precise intervals, creating a chain of signals stretching from Earth's orbit to the outer solar system. They weren't natural objects anymore, if they ever had been. They were beacons. Infrastructure. They've been here for months, Chin told the hastily assembled scientific panel via video conference. Maybe longer, building quietly, observing. The September surge wasn't invasion. It was construction. They were putting communication nodes in place. For what? Demanded General Patricia Okonkwo, representing the U.S. Space Force. For what's coming after Artifact 1, Chin replied, look at the data from Swan. Before it left the solar system, it transmitted one final burst back toward deep space, not a random direction, toward a specific coordinate. She pulled up a star chart. Tau Ceti, 12 light-years away. If something left there when Swan sent its signal, and if it can travel like these objects can travel, the implications hung in the air like a held breath. NASA's Jet Propulsion Laboratory, November 3rd. Dr. James Okoro was reviewing OSIRIS-APEX's pre-encounter checklist with a simulation through an impossible result. Apophis's trajectory had changed. Not by much, just 0.003 degrees of arc. But for an object whose path had been calculated to within centimeters, any change was seismic. More troubling, the shift brought Apophis infinitesimally closer to Earth's path in 2029. Still safe, still passing outside satellite orbits, but closer. Okoro ran the calculation again, factoring in the new data. Then he ran it for 2036, when Apophis would return for another close pass. His coffee cup slipped from nerveless fingers. "Oh, God," he whispered. The equation was elegant, terrifying, and unmistakable. If Artifact, one docked with Earth as predicted, if its gravitational mass matched the estimates, if it remained in Earth orbit for more than 6 months, Apophis would pass through a different gravitational keyhole in 2029, not the one that led to a safe 2036 passage, the one that brought it back. To impact, April 13th, 2036 suddenly became humanity's deadline. The world fractured along familiar fault lines. Russia and China insisted Artifact, one be considered hostile until proven otherwise, quietly repositioning military assets. The U.S. called for a unified response while simultaneously launching 3 classified payloads aboard SpaceX Falcon Heavy rockets, payloads that repositioned into remarkably convenient orbits for intercepting something approaching Earth. Europe advocated for peaceful contact, but hedged by accelerating their own lunar base construction timeline. India's space agency went radio silent, then announced they were pursuing independent verification protocols. Meanwhile, the scientific community worked in frantic parallel. Every major observatory contributed data. Radio telescopes listened for any conventional transmission. Particle physics labs worldwide synchronized their detectors, hoping to capture more quantum messages. Riley's team decoded fragment after fragment of the original transmission. The mathematics was beautiful. Elegant solutions to equations that had plagued human physicists for decades. Hints at energy systems that made nuclear fusion look like rubbing sticks together. And buried in the recursive patterns, something that looked disturbingly like a blueprint for a consciousness transfer protocol. They're not just asking if we're equals, Riley told Commander Volkov during their daily briefing. They're offering to make us equals. This technology, Elena, if we could understand even 10% of it, then we become something different. Volkov finished quietly. Something post-human. Is that what scares everyone? Not invasion, but evolution? Volkov gazed at Artifact, one through the cupola. What scares me is the countdown. Why 23 days? Why not arrive and wait for us to respond? Unless they're not just coming to Earth. Chen's voice cut in over the calm she'd been listening from Houston. They're coming to Earth to meet something else. Look at the timeline. Artifact. One arrives November 20th. Swan's transmission to Tau Ceti was sent September 11th. If a response left Tau Ceti immediately, traveling at the speeds we've observed. Riley's fingers flew across her keyboard. The calculation took 3 seconds. They arrived November 21st, she breathed. 23 days from the first transmission. They're not giving us time to prepare. They're synchronizing arrival times. Earth isn't the destination, Volkov said. Earth is the meeting place. November 6th brought the first casualty of the crisis. An Indian physicist named Dr. Rajesh Sharma, working independently on the quantum transmission, claimed he decoded a warning embedded in the mathematics. Before he could present his findings, his laboratory experienced a catastrophic power surge. Sharma died instantly. His research notes vanished from every backup server. Accident, sabotage, or something else. Conspiracy theories erupted across social media. Governments denied everything. And quietly, very quietly, other physicists working on the transmission began receiving anonymous death threats. In the midst of chaos, an unexpected voice emerged. Sergei Karpov released a video that went viral within hours. Standing in the rebuilt Chelyabinsk Square where he'd filmed the original Meteor, he spoke directly to the camera. 12 years ago, I watched the sky explode. I thought I was going to die, but I lived and I learned something. The universe doesn't care about our fear. It doesn't care about our politics or our borders. What happened that morning wasn't an attack. It was a reminder that we're small, we're fragile, and we're all on the same tiny rock together. He gestured at the sky. Something is coming. Maybe it's a threat. Maybe it's salvation. But whatever it is, we face it as a species, or we don't face it at all. So I'm asking, what answer are we sending? Fear and weapons? Or curiosity and welcome? The video reached 200 million views in 24 hours. World leaders couldn't ignore it. Neither could whoever, or whatever, was watching from Artifact. 1. Because the structure had begun transmitting again. Not quantum particles this time, but something far simpler. A countdown visible to the naked eye, projected onto its surface in light. 14 days. 13 days. 12. And orbiting Earth at the exact altitude where Artifact, 1 would arrive. The September asteroids began rearranging themselves into a new pattern.